Hi, I'm Sean. I'm a H1 maths student and I'm studying maths in college. And I'm here to help you get through your Leaving Cert maths questions. So let's get into it. Okay, so here's our question. We're told that Harry draws a scale diagram of the portion of his garden that is covered in lawn. And here's the diagram below. So each box on the grid is 1 centimeter by 0.5 centimeters. And each centimeter on Harry's diagram represents 3 meters. In order to estimate the area of the lawn, Harry divides the diagram into 8 sections. Okay, so for part A, they ask us to use the trapezoidal rule. So we're going to get that from the log tables. To estimate the area of the lawn using the scale 1 centimeter is to 3 meters. Okay, so first of all, we're just going to write down the trapezoidal rule, and then we're going to break it down and see how it applies to this problem. So here's the trapezoidal rule. I've just written it down and continued it on the second line here, so I hope that's okay. But basically this is used to approximate the area under a curve. And one thing I just think we should double check before we proceed is that our thing is symmetrical, or our area is symmetrical about the y-axis. Because if it is in fact symmetrical, we can just find the approximate area of this region and then double it in order to find the total area of the whole region, including the bottom one as well. And another thing to note here is that this squiggly equal sign isn't a mistake. It's just how you say the approximate equality, so it's like not exact, just in case you didn't know that. So let's now just go and label h and our y values so we can plug in then and find the approximate area. So if we go to the log tables for a second, to page 12 where I got the trapezoidal rule from, clearly h is the gap between the y values. So we have this value h, and you could sort of think of this as the difference, this change in x. So like, let's say you're going from 1 to 2 to 3, then in that case h would be equal to 1. So in our problem, we're told that the gap here is 1 centimeter, but that in real life is actually equal to 3 meters. So then in our case, we're just going to let h be 3. Now going back to the log tables once again, y through to yn is just the heights of the different lines that are drawn. So y1 is obviously the height before the curve actually starts, and then yn is at the end, and then you have these different heights in between. So for our problem, y1 is going to be equal to 0, and yn is going to be equal to 0, and then we're going to have to count up the number of squares. So in this case it's 5, and that would be y1, and we're going to do that for every y through to yn minus 1, which would be over here. So here are the heights of all our different lines, and once again all I've done here is count up the number of steps it took to get to the top of the curve for each a different point. Now the confusing thing here is that in the marking scheme they've chosen to basically double this to account for the bottom half of the curve, so sort of preemptively, and knowing that it was going to be symmetrical. I'm just going to leave that to the end of the question because I think it's clearer to get first of all the area of the curve above the x-axis, so on the top, and then double that. But the order doesn't necessarily matter, so you're going to see that our answer is going to be initially half what they have in the marking scheme, and then we're going to double it afterwards. So now one more thing to note is that we have to adjust these different y values so that they're to scale, because we know that 1 centimeter on our diagram is 3 meters in reality, once again from up here. So we're going to have to triple all our different values. But one thing that could catch you out is that these actual upward steps are only 0.5 centimeters in length. So therefore we're going to be multiplying our y values by actually 1.5, because that would be 1.5 meters in reality. So that's the most difficult part of this over, and we're just going to start our equation for the area now. So the area is roughly equal to 3 over 2, where 3 is equal to h here. Then we have 0 plus 0, because the first and last y values are 0 and 0 from the diagram. And then we have twice times the rest of the y values, but rather than just multiplying it by 2, I'm also going to multiply it here by 1.5, because that's the number of meters it represents in reality. Okay, so now we've added all our y values in, and now we have this big long expression that we can just put in the calculator to find the total area, or at least the top half of the area. So once we plug it in, we're going to get that a is roughly equal to 162. But now we shouldn't forget the last step here, which is to double it, so that we also account for the bottom half as well, because we've only been dealing with the top half up to this point. So our answer times 2 is equal to 324 meters, which is our final answer. And actually, on second thought, now that we realize that it's area, which should be meters squared in both cases as opposed to meters. And that's it for part A. Nothing too bad about that. You'll notice that this curve actually, and this shape, is symmetrical both about the y and x axis. So in other words, you can draw a straight line down the middle and also a straight line across, such that if you folded it upon itself, it would fold perfectly. And that won't always be the case. Sometimes these curves will be just lopsided and you're just going to have to do the same thing, but it shouldn't change anything really. But curves like this do appear quite frequently in nature. For example, with butterflies and bees and whatnot for wings, and with different things with different curves describing relationships that appear naturally. So if you're interested in maths, then it's certainly something you're going to see quite a lot. But as I said, that's it for part A, and for getting that out, you're going to get 15 marks. So part B is really nice. They just tell us that Nuala can walk at a speed of 1.6 meters per second, and we're asked to write this speed in kilometers per hour. So if we just disregard for a second 1.6 meters and just consider the relationship between 1 second and 1 hour, clearly there are 60 seconds in a minute, and we're going to have to multiply that by 60 minutes for an hour. So the total number of seconds in an hour is equal to 60 squared, and that is equal to 3,600. And you can of course use the calculator here if you need to, but it's not that hard to see if you just think about it. And now secondly, we're going to think about the relationship between meters and kilometers. So hopefully you know that there are 1,000 meters in 1 kilometer, which means that we're going to take 1.6, we're going to multiply it by the number of seconds in an hour, which is 3,600, and then we're going to divide it by 1,000 because we want it in kilometers rather than meters. So we can put that in the calculator. Actually, it just has 1.6 times 3.6, because 3,600 divided by 1,000 is 3.6, and our final answer is going to be 144 over 25, or as a decimal, just by pressing SD, we're going to see that it's 5.76 kilometers per hour. So that seems reasonable. That's a pretty realistic walking speed, and for getting that out, you're going to get 10 marks. And before we finish up, one thing I forgot to mention about part A is that just to make sure that your answer is right, I'd recommend you just count roughly the number of squares and then multiply that by the scale. So 3 by 1.5 for each square. Again, that's kind of going to be time consuming. It might take up 2 or 3 minutes, but if your answer is completely off, then obviously you're going to know that you have made a mistake. So that's just kind of a tip on checking your answer there. And of course, for part B, we know that 5.676 kilometers per hour would be a pretty reasonable walking speed, which is a way to check that this is actually correct as well. But that is it for this question. I hope you did enjoy the video. If you did, there's going to be other similar videos in the description, as well as some other helpful resources for the trapezoidal rule and whatnot. And I'll see you next time.